Hey there, it's Shannon Math Chick Myers, and today we're taking a look at the area between two curves. Always so exciting. All right, this is 7.1 in the Larson and Edwards Early Transcendental Calculus book, and we will check out how to find the area of a region between two curves when you are given the two curves and also some vertical or horizontal lines to bound them. Then we're also going to look at how we would find the area of a region between intersecting curves using integration. All right, so it's always, good to have sort of a basic picture. So if we take a look at just some random area region, and think about what is going on with it. And then we'll just draw a couple of functions. Doesn't really even matter what they look like. Call this guy F. That one looks a little on the shaky side. That one doesn't work for my evil plan. It does, but there we go. This one will be G. And we've got these vertical lines here that are also bounding a region, right? Copy this so you can see what's happening. It's honestly the same kind of concept as if you were to draw a circle inside a square or vice versa, and you would find the area of the bigger one, and then you would subtract the area of the smaller one if you want the area in between. It's really the same idea. So here, the region, the area region that we're after is the one that's bound here in between these four graphs, the two vertical lines, and the functions f and g. So this region R is the region between the curves f and g and the vertical lines x equals a and x equals b. All right. And in this case, if you're thinking of your little rectangles, this would end up being, since we have it drawn this way, and we didn't specify that this was, a function of y, we would have our little rectangle like this, and it would have a width of dx. Cool? All right, so here we go. If we were to take a look at separating this out, this meaning how this region was found, using the area definition that you would have learned in Calculus 1, kind of around the same time you learned the fundamental theorem of calculus, we would end up having that definition basically says if you wanted to find the area of the curve below f. Notice that f is non-negative on the interval from a to b, and then also bound by x equals a to x equals b and the x-axis. And so this would end up being the integral from a to b of f at x dx, right? That whole purple region. And then if you were to take a look over here at the region under G, do you see that the region we made just to the left, the purple region minus the green region, is going to be the blue region that we desire? And so this region is going to be the integral from a to b of g at x dx. And so the area of our blue region will equal to, A is for area, the integral from a to b of the purple, which is f at x dx, plus, minus, my bad, the integral from a to b of our green region. That makes our green region. And so putting it in one happy integral, you have the integral from a to b. And notice that f is greater than or equal to g along the interval a to b inclusive. And so the difference between f and g will always be positive. So that means we can say f at x minus g at x all in one integral with respect to x. Cool, cool? All right, so we'll go ahead and write it here so you have it in a wonderful box. If f and g are continuous on the closed interval from a to b, and g at x is less than or equal to f at x for all x in the closed interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the integral from a to b of what we put up there, f at x minus g at x dx. So when you're looking at area and your triangle is pictured as above, where you're making infinitely many subintervals on your x-axis, right? You look at topmost minus bottommost. And sometimes that changes when we get into intersecting curves. If you're looking at a function of y, where y is the independent variable and x is the dependent variable, then it would be the picture you would have your rectangle would be representing a change in y. So we have an example of that to come. But this is just giving you a general example in terms of x. Groovy? All right. Now, let's take a look at an example. Examples are always wonderful, right? So, how it works. Finding the area of a region between two curves which don't intersect using integration. So, a lot of times what will happen, a clue here will be you'll either have two vertical lines or two horizontal lines. And that will clue you in to, you don't have to worry about finding your limits of integration. They've been given. So let's take a look at this graph. I don't think it gets to be very high numbers. All right, so each unit is a half, or each square is a half unit. So here we go. We have f of x is negative 4 over x cubed. So I'm going to go ahead and find f at the vertical lines. And then that'll give me negative 4 over negative 3 cubed is negative 27, which is just 4 over 27. Now we can go ahead and plot that point. 4 over 27 is pretty darn small. A half would be what, 13.5 over 27. It's even less than a quarter. So if we go back to negative 3, it's going to be pretty close to the x-axis. Now, f at negative 1 will be equal to negative 4. Negative 1 cubed is still negative 1, so that'll be up at 4. So we'll have a point here. And then, just to get a feel for what it looks like in the middle, why don't we find f at negative 2, just for fun? That would be negative 4 over negative 8, which is positive a half. And that'll be right there. So we're going to have something that looks like that for our graph of f. Now, the other graph, it's one of those so easy it's hard things. We have y is 0, right? And so y is 0 between these lines, between these bounds, is just going to be like that, drawing on that x-axis. And then you've got these vertical lines. So it turns, you've got this vertical line here, this vertical line at x equal 1, negative 1, sorry. So we have x is negative 3 and x is negative 1, taking from these guys. And so our area region is in here. Now, topmost graph is the blue one, right? So if we go ahead and we set it up exactly as the formula, our area would equal to the integral. A is negative 1, B is negative 3, and then we're going to have our blue graph, which was negative 4 over x cubed minus our green graph, which is 0, and that's with respect to x. If we were to draw the little rectangle in here, it would look like this. This would be the dx, change in x. So then, making this a little more friendly for integration, there's a couple things we can do. I don't know about you, but all those negatives are easy to get lost. So I don't know if you remember, you can flip the limits of integration if you flip the sign of the integrand, which would make it positive inside. So this is an equivalent integral. I'm going to write the x using a negative exponent. I didn't lose the negative on the 4, it went away because I flipped the limits of integration, and then dx. So now integrating, be careful, don't mix it up with differentiation. You increase the power by 1, which gives us negative 2, and divide by that. And then we are going from x is negative 1 to x is negative, nope, we flipped it, sorry, my bad. Going from x is 1 to x is 3. Now I'm going to clean this up just one more time. We'll end up getting -2 times (1 over x squared) from x is 1 to x is 3. And so our area will be -2 times upper limit of integration will give us 1 over 3 squared, which is 9. And then lower limit of integration is 1, and then you square the 1, you just get 1. And so our area will be -2. 1/9 minus 1 is 1 minus 9 all over 9, because 9/9 is 1. And so our area will end up being -2 times -8 over 9, which gives us a result of 16/9 square units for the area. Groovy? All right. Next up, I always liked these problems. Fun math. All right, so next up we have an f of y. So f of y is like saying x equals, right? So if you're more comfortable, you could write it like that. So we have sort of a clue here. We have these horizontal lines, right, that are going to serve as limits. And so for this one, again, I don't think we're going to have to worry about super big numbers. So I'll have the same scale. And then we have y equals -1 as one of our lines. Whoops, do that in red. And we have, so that one's y equals 1. And then we have y equals 2. And then our f of y equals y squared plus 1. So that's going to be like a sideways parabola, right? Sideways parabola. So here, if I put in, let's find out what we have. So if I put in -1 for y, I will get -1 squared plus 1, which will end up being 2. So that means I'm going to have the order pair 2, -1, because it's that sideways one. Now f at 2 will be 2 squared plus 1, which is 5. So I'll have an order pair at 5, 2. And then if you want to just kind of get a feel, you know, for how that curve is going to look, if you're not super comfortable with conics, you can always find out what is f at 0 going to be. So if you plug in 0 for y, you're just going to get 1. So we'd have the point 1. So x would be 1 and y would be 0. And so we will have our little parabola here. You've got symmetry here. So you can even get another point, because that is our axis. And then that's our first graph. Cool. So that is F. Now y is just g at y equals 0. G at y equals 0 is the same as x equals 0, and we'll just go along those bounds. So this is the line g at y equals 0. So our area of interest is rightmost minus leftmost. And so you go below or to the left of that blue bound, which is made up by F, and you go until you hit the y-axis, which is the line x is 0, or g of y is 0. Groovy? All right, so let's take a look at what we get for the integral. So our area will this time be rightmost minus leftmost. So we'll have the integral, and this time if you want to draw in your little rectangle, this is a situation where you'll have dy. And so we will get the integral from -1 to 2. Our rightmost graph is the blue one, which is y squared plus 1. And then our leftmost graph is, again, 0. It doesn't always work out like that. And be careful, this time it's with respect to y, because we're dealing with functions of y. So simplifying, we have the area will be the integral from -1 to 2 of y squared plus 1 dy. And then integrating, we will have 1/3 y cubed plus y. And now our limits of integration are about y. Y is -1 to y is 2. So for our upper limit of integration, we'll have 1/3 times 2 cubed plus 2 minus our lower limit of integration. We'll have 1/3 times -1 cubed plus -1. This is going to give us 8/3 plus 2 plus 1/3 when I distribute the minus through, and plus 1. So we will have 9/3 when I add the fractions, plus 3, which is 3 plus 3, which is 6 square units. Awesome. All right. And so next up we have area of a region between intersecting curves. So with these, it's a little more complicated because we have to find the limits of integration on our own. So sometimes just by graphing the two curves on the, if you're doing it by hand, you find the limits of integration where they intersect. Sometimes you might need to use a graphing calculator. These examples aren't really such that you should need to. And then other times you need to set the equations equal to each other and solve solving that nonlinear system of equations. So sometimes we need to find the limits of integration by setting the functions equal to each other and solving the resulting system of it's often nonlinear equations. And let's see how it works. So first we're going to sketch the region. This one, I'm looking that we have x squared. So actually, you know what? Let's just go through and let's find the limits of integration. This is why you solved systems of nonlinear equations in college algebra. Whoops. I don't know why I was writing integer. Find limits. Oh, because of integration. Integration. Excellent. So to find the limits of the integration, we're going to set f, so we'll stick with those same colors, and we're going to set f equal to g, and then solve. So f is equal to x squared, right? And then g is equal to 6 minus x. So this is quadratic in form. So we want to get all the variables, everything on one side and then 0 on the other. So we'll have x squared plus x minus 6 is equal to 0. This is factorable. You could always use the quadratic equation if you don't know how to solve it, but it factors as x plus 3 times x minus 2 is 0. I just know that a negative product means you have different signs. I needed something that multiplied to negative 6 and that when you combine like terms was positive. That's why I chose the positive for the 3 and the negative for the 2. All right, so this means that we get x is negative 3 or x is 2 because we set each of them equal to 0 and solve using the zero property rule or zero product property. All right, so now that we've done that, let's work on the graph. If one of my bounds is going to be negative 3, I know that the blue graph is x squared, so it's going to be up there at 9. So I think but our x values don't need to be that smushed. So I'm going to keep the scale for the x values as 1 square as a half a unit, but for the y values, I'll switch it over to where each box is 1 unit. So the blue graph, all right, so f at negative 3 is going to be negative 3 squared, which is 9. So I'll have 1, 2, 3. I'll have a order pair there. And then f at 2 is equal to 2 squared, which is 4. So 1, 2, 1, 2, 3, 4. And then, like I said, getting something in the middle would be nice. So I'll just find f at 0 is 0 squared, which is 0. And then we have symmetry. And so we can get kind of our nice parabola graph. something like that. Now the g of x will be really easy to graph because we figured out that they intersect at -3 and 2. So just to show you, g at -3 is 6 minus -3, which is 9. So like I said, we'll get the same point here. And g at 2 is equal to 6 minus 2, which is 4. And we just have 2 points, and that's all we need to graph our line. Good so far? Awesome. All right, and so our area region is in here, and do you see how it's all contained? You don't need any vertical lines to seal up that area region. All right, excellent. Now we have, if you want, these are functions of x. So I'll just draw in our little rectangle. This is the width of that rectangle is dx. It could be anywhere in there in that region. And so finding our area, the topmost graph is the pink graph. So our area will be, so actually this was for sketching the graph, because you really need to sketch the graphs to find out which graph is going to be on top and which graph is going to be on the bottom, or with the function of y, which graph will be to the right and which one will be to the left. And then number 3, find area. And so our area will be the integral from -3 to 2. Topmost graph was 6 minus x, minus bottommost graph, which was x squared, and that's with respect to x. So that gives us an area of, actually I'll simplify it. We'll have -3 to 2, limits of integration, and then we'll just have 6 minus x squared dx. So we will get 6x minus 1/2 x squared minus 1/3 x cubed once we integrate, and we're evaluating that from x is -3 to x is 2. So we will have area equals, the upper limit will be 6 times 2 minus 1/2 times 2 squared minus 1/3 times 2 cubed, and then subtracting that lower limit, we'll have 6 times -3 minus 1/2 times -3 squared minus 1/3 times -3 cubed. Continuing, that will give us 12 minus, let's see, 4 over 2 is 2, minus 8/3, minus a minus 18 is plus 18, and then -3 squared is 9. You'd get a -9/2, but the sign would flip to a +9/2. And then you'd have a -27 divided by 3 is -9, flip the sign, and we have, do we have a +9? Oh no, but then it would go minus again. Do you see that? Because there's a triple negative. All right. Okay, so I'm going to combine the whole numbers here. So let's see. do you see that negative 9 and negative 2 is negative 11, plus 12 is positive 1, plus 18 is 19. And then we have, let's see, 6 would be the common denominator, so minus 16 sixths, and then plus 27 over 6. And then we're going to have to get 19 in terms of 6. So 20 times 6 is 120, and then minus 6 would be 114. These two combine to be positive 11 over 6. And then the area will be 125 over 6 square units. Good? And then you can always double check your work, by punching it into the calculator if you have access to it. If we want to go into math, and we want to do function integrate. Our limits of integration go from, negative 3 to 2. And then we had 6 minus x squared. And that's with respect to x. And enter. Now, if you want to change something to a fraction, you just hit answer fraction. It'll go to answer fraction, and we get 125 over 6. So woohoo, we did it. And that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you do like the show, please click on that like button, subscribe to my channel, and or share the video. Have a good day. Bye.